Thank you. Thank you very much. Of course, it's a great honor and pleasure to speak at this wonderful Congress. What I will talk about is an overview of a line of work that I've been doing for a long time. So there will be kind of a panorama of several types of results, joined with several people that will be mentioned along the way. Yes, this works. Let's start with just some basic notation and setup, mostly for the experts. So the talk will be about Calabi-Yau. X will be the notation for the space, which will be a complex manifold of n dimensions, and it will be immediately be compact, so closed without boundary. So I will give some examples in the next few slides. This complex manifold, so it's covered by charts, the transitions are holomorphic, and you can talk about metrics, in particular Hermitian metrics. That would be the analog of a Riemannian metric in this complex world. Very important subclass of Hermitian metrics are what's called Kähler metrics. So a Kähler metric is a Hermitian metric, which you can, oops, yes, wrong button. You can, in local coordinates, write as a Hermitian tensor GJK bar, positive definite, such that if you cook up a two form from the Hermitian metric in this way, omega, so you take the metric, you multiply by this dz wedge dz bar k, and put an imaginary unit, then this becomes a real two form, and the Kähler property means it's requiring that the exterior derivative is zero. So it's just some condition, in fact, a partial differential equation, a system of partial differential equations for the first derivatives of the metric components GJK bar. This two form has a 1 dz and 1 dz bar. This is what we call type 1,1. This condition, of course, is written in local coordinates, but if you change coordinates, this property of being 1,1 is invariant, so we call it a 1,1 form. All right, so we will always assume that X admits a Kähler metric, and once you have a Kähler metric, you can look at the cohomology class of this two form in the RAM cohomology because it's closed. So the RAM is closed modulo exact, H2, and there is, in fact, a distinguished subspace, H11, which is the classes which contain a closed real 1,1 form. So it's pretty obviously a linear subspace of H2. Because everything is compact, these linear spaces are finite dimensional, and by definition, the class of omega lies in this subspace. If you now vary omega, look at all possible Kähler metrics on your manifold, all of them, this is a huge space. In particular, it's, in whatever reasonable sense, it's infinite dimensional. But if you only look at the shadow in cohomology, so all the cohomology classes of all the possible metrics, this traces out an open convex cone in this finite dimensional vector space. So this is the, if you want, parameter space of cohomology classes of Kähler metrics. So this is the Kähler cone of the manifold. So all of this story does not have any analog in Riemannian geometry because for a Riemannian metric GJK, you can't make dxj wedge dxk. You would just get zero because one is skew-symmetric and the other is symmetric. So it's a special property of the complex world. Oops, all right. So many nice things happen when a metric is scalar. In particular, there's some linear algebra facts. For example, the volume form, the Riemannian volume element is equal to the wedge product of omega with itself, the maximum number of times, which is n. By the way, n is the complex dimension, so it's modeled by Cn. So as a real manifold, the real dimension is 2n. So this is a 2n form. And this factor of n factorial, I'm going to ignore it very soon. So if you want to be compatible with the Riemannian world, the volume element would be omega to the n divided by n factorial, but I will drop the factorial from the formulas. And then there is a much deeper differential relation formula, which is a formula for the Ricci curvature tensor. So the Ricci curvature comes from Riemannian geometry, is a trace of the Riemannian tensor, Riemann curvature tensor. And for a Kähler metric, the Ricci tensor is also type 1,1, or has a Hermitian property. So in coordinates, you can write it as Rjk bar. And this has a very, very nice formula in local coordinates. It's just this complex Hessian operator, dzj, dz bar k, of log determinant of the metric tensor elements. So it's kind of remarkable that such a simple expression gives you the Ricci curvature. If you go to a Riemann geometry textbook and look for the formula for RJK, it's usually a much longer expression with many terms, and it does not simplify to anything like Hessian of log determinant. So the Hessian of log determinant does not define a tensor in Riemann geometry. So anyway, this works, and even better, you can make it into a 1-1 form, 2 form, in the same way that we did for the metric tensor. So the Ricci form, denoted by Ricci of omega, is just obtained by taking the Ricci tensor, multiplied by this dZj dz bar k. Again, there's an imaginary unit, and you get a global 2 form. In fact, 1-1 form. And the second Bianchi identity gives you that it's declosed. I mean, it's also kind of obvious by this expression anyway. So it has the same properties as omega. It's a closed real 1-1 form. And therefore, it defines a cohomology class also in the same H11. And this cohomology class actually is independent of omega. This was actually already observed in the 1930s in the original paper of Erich Kähler, but it's now commonly attributed to Chern. So the cohomology class is called the first Chern class of the manifold. And the reason why that's true is you just take the difference of 2 Ricci curvature forms of 2 Kähler metrics. So they will have these 2 expressions for G and G tilde. And you realize that, log that GPQ bar is not a globally defined function, because when you change coordinates, it changes. But when you take the difference of 2, so log that of one minus log that of the other, there is a global smooth function. So denoted by this log of the ratio of the volume elements. So this is a global smooth function, and then this formula tells you that the difference is 2 derivatives of that function. So it's in particular d-exact. So this should be more or less clear now. So the cohomology class does not depend on the choice of the metric. And so Calabi-Yau for this talk will be compare Kähler manifold, meaning compare complex manifold that admits some Kähler metric, such that the Furchen class that we just defined vanishes in real cohomology. So it's the same as vanishing in H11, right? So this is not the strict definition of Calabi-Yau. I will elaborate on that later. There are many things people call Calabi-Yau. This is the kind of most liberal definition of Calabi-Yau that comes from the original paper of Yau, as I will discuss in the next slide. So naturally, you define something. So this just means you have a Kähler manifold. You take any Kähler metric you want. Oops. Oh, no, sorry. And compute the Ricci curvature form, and that's exact. So it's some kind of global condition on the Ricci curvature. All right, so the simplest example you could possibly think of is just to take a torus. So Euclidean space modulo a lattice, which is a additive subgroup isomorphic to z to the 2n, acted by translations. So as a smooth manifold, this is just what you call T2n, the 2n dimensional torus. As a complex manifold, the choice of lattice does matter. So you get different tori depending on the lattice. Nevertheless, there are Calabi-Yau, for example, you could say that there is a Euclidean, in fact, many Euclidean metrics on Cn, constant coefficients, so very much Kähler, d omega will be 0. And since they're constant coefficients, they're invariant by translation, so they descend to Kähler metrics on the torus with no curvature. So in particular, Ricci is definitely 0. These would not be called Calabi-Yau by many purists. So better ones are so-called K3 surfaces. One way to define them is just to say that there are Calabi-Yau of dimension 2, complex dimension 2, which are simply connected. So it's just a definition, but there are many, many examples. For example, this equation in projective space P3 over the complex numbers, everything defines a K3 surface. And there will be more examples later. Here is a picture of a different one. Oh, no, sorry, I think it's actually a variant of this one in P3, but it's only the real points which are pictured. So you see kind of a surface in R3 instead of a complex surface in P3. There are also certain K3s admit a free holomorphic action of Z2, and the quotients are called Enrique surfaces. here is a picture of the, actually something with singularities, but a singular model of an American surface. And anyway, these are also Calabi-Yau with this definition. And you can take hypersurfaces in Pn+1, generalizing this example of the zero locus of one homogeneous polynomial of degree n+2. Then what you get is Calabi-Yau. This is a simple calculation in algebraic geometry using the adjunction formula. For example, this famous Fermat-Quintic threefold in P4. This again is a cheating picture of some parts of the real points of a Calabi-Yau threefold projected many times to fit as a kind of two-dimensional object in R3. Can we classify Calabi-Yau? So Calabi-Yaus are one of the basic building blocks of in the birational classification of complex projective varieties. So they form a very interesting class to study. Up to a finite cover, if you have a Calabi-Yau with my definition, there is always some finite cover which has a never vanishing holomorphic n form, capital omega. And again, some people don't like the finite cover, then just restrict the Calabi-Yau definition to having this holomorphic n form already. So this is actually it's quite a non-trivial statement, but it's true. And the Calabi-Yaus of dimension 1 are actually just tori. So the tori C mod lambda, also known as elliptic curves, where we fix the origin. And this is, I don't know, work of Abel and Jacobi. And Kodaira classified Calabi-Yaus of dimension 2, and he proved in the 1960s the list is given by 2 tori, again, C2 mod lambda, finite quotients of 2 tori. Here is the simplest one I could think of. They take the square lattice in C2, and this very explicit involution, Z1 plus a half minus Z2, you can check that there are actually no fixed points on the torus, and the quotient is a Calabi-Yau two-dimensional manifold. And K3 surfaces that I defined before, and their quotients, which are just this Enriquez. In particular, in each of these cases, you can go much deeper in the classification, especially the case of K3, maybe the most interesting one. And it follows from this deeper study that there are only finitely many homotopy types, say, for these Calabi-Yau surfaces. I mean, in dimension 1, there was only one homotopy type, and here, finitely many. And this is one of the main questions which is not known to be true, whether this finiteness of say, topological types holds in higher dimensions. So if you fix dimension, say 3, are there finitely many Calabi-Yau threefolds up to your favorite condition, say homotopy or diffeomorphism or whatever you prefer? None of them is known. So, there are a large number of examples known by various constructions as, say, complete intersection in product of weighted projective spaces, and physicists were very interested in this in the 80s and 90s. They developed a lot of technology to find many, many examples. But still, the number you get is large, but so far finite. So why I call these Calabi-Yaus? So because of the following theorem of Yau, conjecture by Calabi, that if you have a Kähler manifold, a compact, then it admits a Kähler metric with 0 Ricci curvature. This is this Ricci flat Kähler, if and only if it's Calabi-Yau. So that's, if you want, the reason for calling Calabi-Yau is because they're the ones that admit Kähler metrics with no Ricci curvature. More precisely, he proved that if you have a Calabi-Yau and you fix a Kähler class, so a class of some Kähler metric in the Kähler cone, then there is a unique representative omega tilde, which is a Kähler metric in that correct class and with 0 Ricci curvature. So it's an existence and uniqueness theorem for Ricci flat metrics. And interestingly, while these Ricci flat metrics are geometric objects, things you might want to construct with geometry, they are actually constructed with analysis. So the omega tilde is obtained by solving a nonlinear PDE called the complex Monge-Ampere equation, which looks like this in complex coordinates. It's the determinant of the fixed metric G, which is this omega here, plus the complex Hessian of a function phi. Phi is a global function. And then the right-hand side is some smooth positive function f times the fixed determinant. And the new Kähler metric would be this original plus this complex Hessian of phi. And this should be positive definite. And so this equation can be solved uniquely. And the solution, though, is never explicit except on tori. So on tori, you can write down the solution explicitly, but otherwise, there's no explicit solution. So because of that, it's actually quite interesting to study what happens when you take limits of this matrix. So what I want to study in this talk is the degenerations where the Kähler class moves. So we are having a fixed Calabi-Yau with this, its scalar cone, and you fix a point alpha on the boundary. And you can assume it's non-zero, otherwise the whole discussion becomes very simple. So you have a non-zero point on the boundary of this cone, alpha, and then you want to approach it from the inside of the cone. So let's say with a continuous path, alpha t, t defined in, let's say, a unit interval, which at 0 is this endpoint, and for t positive is inside. So you move from inside the Kähler cone to some point on the boundary. So this is one simple enough way to construct degenerations of this matrix, because we can just apply Yau's theorem for each t strictly positive. For each t strictly positive, there's a unique Ricci-Flat metric omega t in the correct class. And these metrics have to degenerate in some way because the limiting class alpha is not in the cone. Remember, the cone is open. So the point on the boundary is not a Kähler class. There is no Kähler metric in that class. So the omega t cannot converge smoothly to a strictly positive limiting Kähler metric. So something has to degenerate. And the classical question, which appears in one of Yau's lists, is to understand the behavior of this matrix when t goes to 0. So as a kind of warm-up, a basic result I proved a long time ago and independently Yuguang Zhang is that if you look at the corresponding Riemannian matrix GT, then the manifold, you can talk about the diameter of X, which is the largest distance between 2 points. And this diameter does not go to plus infinity. So when you approach this limit, the diameter stays bounded above. So that's useful enough information, especially in Riemannian geometry. In particular, you can apply all the result of Gromov, because these metrics have Ricci equal to 0, and they have an upper bound for the diameter. So Gromov's pre-compactness theorem will give you subsequential limits in the Gromov-Hausdorff topology, so as metric spaces. So there is some simple limit that you can try to take just using this diameter estimate. So some, yes. Yeah, actually, it already appears in the next slide. Yes, it is important very much, but I will discuss when it matters and when it doesn't. Sorry, it's down here. So yes, it's a very good point. Yes. So some questions. First of all, there's the kind of geometric problem. So you have this family of Einstein manifolds. The Einstein constant is 0. So Riemannian metric with 0 Ricci curvature. Can you take the geometric limit? I mean, for example, say as metric spaces in the Gromov-Hausdorff sense. I just told you that subsequentially you can, but can you take a limit without subsequences? And can you identify this limit? And is this limit a complex space? Meaning, is it homeomorphic to a, say, complex analytic variety or a complex manifold if you're very optimistic? That would be the kind of geometer's question. Then the analyst's question would be to look at the PDE. So write down the PDE, so fix some reference scalar metric omega x throughout the whole talk. Omega x will be some fixed metric. For simplicity, I assume it's volume 1 and Ricci flat. You can achieve this by Yau's theorem plus scaling. And then you need to fix smooth forms representing these classes. And they should vary continuously in the time parameter. You can do that. Then your solution is written as the reference smooth forms plus dt bar of a potential phi t. Phi t is unique up to a constant. The constant is fixed by normalization. For example, the maximum value is 0. And the Monge-Ampère equation from before is exactly this one. So this is the determinant, okay, written as a top wedge product, is equal to a constant times the determinant of the fixed one. And the constant is just the total volume up to some factorial coefficients. And this total volume is just the integral of omega t to the n, and it converges to the integral of alpha to the n, the limiting class integral. So you could ask then, okay, I have this nice family of PDEs. For t strictly positive, I have a smooth solution. They also vary continuously in t. And what happens when t goes to 0? Can you prove a priori estimates for phi t that do not blow up when t goes to 0? Can you take a limit? And once you got a limit phi 0, how is this related to the geometric limit from part 1? So are they kind of the same? And yeah, the question that Boo was asking, does the limit depend on the choice of path or only on the limiting class alpha? And as we will see, there are actually many interesting examples of this setup coming from algebraic geometry and from dynamical systems, so holomorphic dynamics. And I'm not going to mention this explicitly, but there are other applications of this type of ideas to the case where you change the complex structure of the Calabi-Yau. This is related to the Strominger-Yau-Zaslow conjecture, and also to Kähler-Ritchie flow, as well as to questions in dynamics called the Kummer rigidity. So I don't have time to discuss these other applications, just to say that perhaps you find this a kind of specialized question, but the same kind of ideas are useful also in related contexts. Okay, so so the title of the talk was collapsing, right? So I will just spend one slide on the non-collapsing case, which is the case when the limiting class has positive self-intersection. So that means that the Ritchie-Flat matrix, the total volume, does not go to 0 because it's approaching a positive number. That's what we call volume non-collapsed. So this case turns out to be much easier to understand than the other case is equal 0. So this integral is non-negative by construction. And so long time ago, again in 2007, and then later with Tristan, who's here, we obtained the smooth convergence away from a small bad set. So if you take the union of all V, where V is let's say closed, complex submanifold of X, in reality, you should allow V to have singularities, so really it should be an irreducible closed analytic subvariety. And take the union of all these, let's say, submanifolds, where the limiting class integrates 0. So these are the ones, submanifolds whose volume in the Ritchie-Flat metric is going to 0. So these are submanifolds that are shrinking, or subvarieties that are shrinking. Take the set theoretic union, then this set theoretic union is actually a closed analytic subvariety. It has maybe many irreducible components, but finally many. And away from this, you have smooth convergence to a Ritchie-Flat metric on the complement of this subvariety. This limit is independent of the path, so you always get the same limit. So this is in a sense, the analyst's question. And so the phi t have C infinity estimates on compact sets. And the geometer's question, Rong and Gongzhang proved that the Gromov-Hausdorff limit exists without subsequences, and it's identified as the metric completion, so it's isometric to the metric completion of this smooth limit. And Jan Song proved that if the limiting class is rational, so that's the extra assumption, then this limiting metric space is homeomorphic to actually a projective variety. So it has a complex structure in some sense. And also, when you did this completion, you complete it by adding some stuff. The stuff that you add has Hausdorff codimension at least 4. So you add some very small stuff. It's all nice and good. You will complain that the last part has an extra assumption. So indeed, it would be nice to remove it. For this, you would need this conjecture that I formulated with Simeon Philippe some time ago. Namely, that if you have a Calabi-Yau and a class on the boundary of the Kähler cone with positive volume, this integral here, then actually this class is the pullback of a Kähler class from some possibly singular Calabi-Yau variety. So there is a holomorphic map from X to some Y. Y is a singular Calabi-Yau space. I mean, maybe smooth, but usually singular. And this needs to be defined properly. And then you need to define Kähler metrics on a singular Calabi-Yau space. After you define all these things, your class should be the pullback of a Kähler class from the base. So this conjecture is almost certainly correct because there are many instances where it's true. In particular, it's known in dimension up to 3. So dimension 2 was my paper with Simeon. Dimension 3, Andreas Oehring. It's true if alpha is rational. This is a very classical paper of Kawamata in birational geometry. It's also true if the manifold is projective. This is very recent work of Chris Hakon and Om Das. So presumably they are working on the general case. So hopefully it will be settled soon. And the point is, if you can prove this, then that's exactly what's needed to run this Jansong argument. It will give you the same results, the homeomorphism in general. And it will also give you a global L infinity bound for the solution, which, sorry? Complex. Yeah, always complex, yes. Yeah. So real 6 volts. Oh, in this one? Oh, sorry. This is real. Yes. Yeah, I misunderstood. Yeah, this is a real. Yes. So complex 2 in some sense. Yeah. Okay. So let's move on to the collapsing case. So the collapsing case would be when the limiting class has 0 volume, or equivalent the Ricci flat matrix, the volume is shrinking to 0. So you would ask, oh, sorry, I forgot to say that there are many examples of this setup. The simplest examples are K3 surfaces called a Kummer, and there they come by taking a 2 torus, I mean C2 mod lambda, quotienting by an involution which has fixed points, and then blowing up the fixed points. You obtain a K3 surface with 16 special rational curves. Those 16 rational curves are this set S. And then on this Kummer, you perform this construction and this theorem applies. And it was actually proved much earlier by Kobayashi, Todorov, and Lebron-Siman. So we recovered that example in particular. Yes, so for a 0 volume, again, you would like first to have some nice class of examples to see what you're talking about. The simplest examples are where you have a, let's say, with quotation, fibration structure. So I will qualify this now. So namely, suppose your Calabi-Yau has a surjective holomorphic map with connected fibers onto a lower dimensional analytic space, which if you don't like analytic spaces, just say compare complex manifold and everything will be fine. And I want it to be lower dimensional and not a point. So M will be the dimension of the base, strictly between 0 and N. So if I have this map and I take a Kähler metric downstairs and I pull it back, then it satisfies all my requirements. It's easy to see that it's upstairs, it's on the boundary of the Kähler cone, and the total volume is 0. Here you use that M is strictly less than N. M equals N was in some sense the previous, was this one here. This was the case M equals N if you want. All right, so these classes I shall call semi-ample. Semi-ample means this. And why did I call it a fibration? Because you can take this base Y and collect all the singular points of Y, if any, and also all the critical values of this map, call this D, the discriminant locus. It's a closed analytic subvariety. Take the pre-image S, called the singular fibers. It's a closed analytic subvariety. So D and S are very small sets, in particular rectifiable Hausdorff codimension 2, real Hausdorff codimension 2. And if you remove them, your map is very nice. It's a proper holomorphic submersion. In particular, in the C-infinity category, it is a fibration in the usual sense. So F is basically some kind of fibration with singular fibers. And the base also can have singularities. And the fibers of this fibration, the smooth ones, are automatically Calabi-Yau of dimension n minus m. So you have a Calabi-Yau total space, fiber by Calabi-Yaus of smaller dimension with some singular fibers. And then the base. The base does not have to be Calabi-Yau, by the way. These smooth fibers are easily seen to be pairwise diffeomorphic. So it's just one smooth manifold, but the complex structure can be changing. So they can be different as complex manifolds. So these fibrations or semi-ample classes are very easy to construct in algebraic geometry. For example, products would be the stupidest one, namely Y should be Calabi-Yau in the case. The fiber should be also Calabi-Yau. So take the product of two Calabi-Yaus and project it to a factor that fits into this description, but it's a very degenerate and you can say trivial case. Non-trivial cases will be elliptic fibrations where X is a K3 surface which admits non-constant holomorphic map to P1. So then this picture is exactly this, and the generic curve fiber is an elliptic curve. And the collapsing setting that I discussed was studied here by Gross and Wilson in a famous paper in 2000. There is a higher dimensional version of this K3 picture for hyperkähler manifolds, which have a holomorphic Lagrangian fibration onto half-dimensional projective space. And there are many other fibrations where the fibers are not tori. So I should say that these fibrations, the fibers are tori, but there are many other ones where the fibers are arbitrary Calabi-Yaus. And conjecturally, you always have this fibration if your Calabi-Yau is projective and the class on the boundary with this property is rational. So if you have a rational class, a conjecture in algebraic geometry of Bogomolov, Hassett, Schinkel, and Huybrechts from the late 90s says that you should have exactly such a fibration. This is still wide open, even in the hyperkähler case. But there has been a lot of progress in certain cases. So you can think that this fibration should be the case of rational points on the boundary. It's a lie, of course, but roughly speaking. All right, so now what happens in this case? So we are going to take Calabi-Yau with this semi-ample class, so class on the boundary with coming from this fibration. And importantly, I will take this path to be a straight segment. So this is related again to Booth's question. So I take this, this is alpha, the limiting class, and then I add t times omega x. So just approach along a segment. So if you do this special segment, then I proved a few years ago with Hayo-Hein that you do have smooth convergence of the metrics. In fact, you have C-infinity estimates for the potential phi t. So the solution of the Monge-Ampere equation has uniform estimates in with all derivatives away from the singular fibers. So if you are away from the singular fibers, you have excellent estimates of all orders. The limit is pulled back from the base. So upstairs is not a Kähler metric, it's degenerate, it has zeros, but it's actually the pullback of a strictly positive Kähler metric on the base, which has a Ricci curvature equals to a certain Weil-Peterson form, which is non-negative. It measures the variation of the complex structure of the fibers. So Einstein collapses to Ricci non-negative. And the simplest case where this theorem applies was the simplest non-trivial case is the case of Gross-Wilson of a K3 elliptic fibration to P1. So of course they prove this and more in their original paper, but this works in all dimensions. And it's just in the end, it's a theorem about PDE. So it's estimates for Monge-Ampere equations. There is no geometry really in the proof. I mean, there is some setup geometry, but eventually becomes PDE. It's very, very elaborate. It's more than 100 pages. And it follows very earlier partial results by many, many people, including myself. I started to work on this in my thesis. It took a long time to prove this. And I should say that the same estimate, the same theorem also holds for the Kähler-Ricci flow. We did this last year with Hayo-Hein and Lee. So so this is the kind of analyst's question. And about the geometer's question, we do know the answers also. So Song, Ken, and Zhang proved that the Gromov-Hausdorff limit without subsequences is again identified with the metric completion of the base with this limiting metric. Again, there were many partial results before, in particular, in the hyperkähler case, we proved this earlier with Groves and Zhang. And Gabor Sekehidi just yeah, very weak, that's the point, yeah. So the estimates here blow up very fast, yeah, very fast. Not optimal at all, yeah, in general, because the structure of S is kind of arbitrary, so there can be any possible singular fibers. But still, you can prove some much weaker result, much weaker estimate, which is enough to get this Gromov-Hausdorff limit. You don't need to understand too precisely near singular fibers. So Gabor Sekehidi then proved a few months ago that this Gromov-Hausdorff limit is homeomorphic to the base, and also that whatever you need to add to this completion has real Hausdorff codimension, at least 2, which is a sharp. And again, this was known in the hyperkähler case, for example, by our previous work. So the picture looks basically the same as the non-collapsing one. The only difference is that in the non-collapse case, you have a singularity in codimension 4, and here in the collapse case, singularity is in codimension 2. The other difference is that these theorems are much harder to prove than the previous ones. And you could ask what happens to the same theorem if I take a path which is not the straight line. So that's Booth's question. So I take exactly the same setting of a Calabi-Yau and the semi-ample class. So it's pulled back from some fibration. from the base, which is lower dimensional, and I take some other path. So the simplest non-stupid example is again on K3. So take a K3 surface with an elliptic fibration, that's the setup, and assume that you have a so-called twist, which is automorphism of the K3, which preserves the fibers. So it maps every fiber to itself, and it has infinite order. So no matter how many times you iterate, you never get the identity. So these twists are easy enough to construct. They don't always exist, but they exist in great abundance, and it's easy to find such K3 surfaces. If you have this, then you can take alpha, the pullback of a Kähler metric. The base is P1, so up to scaling just Fubini's 2D metric. And because the twist preserves the fibers, this puts back to itself. And if you fix a Ricci flat metric, again, unit volume if you want, you can now iterate this automorphism. This automorphism has some kind of interesting dynamical behavior because it has infinite order. It's doing something interesting. So if you do it n times and you pull back your Ricci flat metric, you divide by n squared. So now instead of a path, this is a sequence, but that's not important. This sequence can be fit into a path if you want. You can also study the path. This sequence here, one can prove that up to some initial scaling, it converges to this alpha, but not along a segment. It converges tangentially to the boundary, so some kind of picture like this. This is the slice of the Kähler cone. So the alpha is here. The previous picture was this one. This one is approaching like this way. This omega n are converging like that. It's pretty obvious that the Gromov-Hausdorff limit is just going to be a point because these are just isometries, this T to the n. So these numerators are Kähler metrics, are all isometric to each other. And then you just scale by something that goes to infinity. So it's just a scaling to a point. So Gromov-Hausdorff, you get a point. That's not good news because in the previous theorem, the Gromov-Hausdorff limit is something on P1, right? It's homeomorphic to P1. And also with Simeon Philip, we proved some years ago that you can take a limit in a weak sense, so-called as currents. The limit is the pullback from P1 you can call this omega 0, but I use a different notation. So some not really metric, but so-called current of this form, Fubini's 2D plus 2 derivative of function u, but u is not smooth. U is smooth away from the images of the singular fibers, but it's only bounded globally. So 2 derivatives of a bounded function is not a pointwise object. Nevertheless, that's the weak limit. And this current is in general not the same as omega 0. So although the limit point is the same, when you approach this way, you get some limiting, the analysis limit. The analyst's limit is this omega 0. When you approach this way, the analyst's limit is some different object, not the same. The geometer's limits are also different, it's just a point. And my student, Junyu Cao, just recently observed that in general, you do not have the higher order estimates. So remember in the previous theorem, as I told you with pain and suffering, we proved the C-infinity estimates. So here, you cannot have C2 estimates for this family of collapsing Ricci metrics. And it's an open problem to see exactly how many derivatives can you control. So less than 2 for sure, but exactly how much we don't know. So already strange things happen even on K3 surfaces with the very friendly class alpha, which is just a pullback of Fubini's 2D from the elliptic fibration. Needless to say, there's a lot more one can try to understand even about this example. The next part or last part is what happens when alpha is not semi-ample. So that's in some sense the last case, right? We discussed the non-collapsing case, collapsing when it's semi-ample. And as I told you, different paths give you different limits. And what happens when the class alpha does not come from a fibration? So you can try to analyze the simplest case of tori. You could call it the trivial case, but it's actually not that trivial. So on a torus, Ricci flat Kähler metric is the same as a flat Kähler metric, which is the same as is induced by a constant coefficient Kähler metric on Cn. and a constant coefficient Kähler metric is just one positive definite n by n Hermitian matrix. So you have this basic bijection correspondence. So talking about Ricci-Feld matrix, you're just talking about Hermitian, positive definite Hermitian matrices. And then each Kähler class then will contain a unique such, correspond to a unique such matrix. And then if the class is on the boundary, that corresponds to a semi-positive definite Hermitian matrix with a non-trivial kernel, so which is not positive definite, right? So it has to have a non-trivial kernel. And observe that if I have a semi-positive definite matrix with non-trivial kernel, the determinant is 0. So that means that you're always in the collapsing case. The determinant is this integral of alpha to the n. It's just the determinant of this matrix. So on tori, you don't see this non-collapsed behavior. You only see the collapsing behavior. The collapsing is in the smooth topology. So the analyst's question is totally trivial here. It's just a bunch of matrices converging. The coefficient converges smoothly to another matrix. So the analysts have nothing to do, but you can ask the geometer what's going on. So the kernel is a linear subspace in Cn, call it K, and you can check if this kernel can be spanned by rational linear combination of vectors in the lattice or not. So there's a dichotomy. So this case here is the case when the class is rational in H2 with Q coefficients, and this is the semi-ample case. So you exactly obtain a fibration from your torus to a smaller torus, and you can factor out the kernel. Your semi-positive definite matrix is the pullback of a positive definite matrix from this factor quotienting by the kernel. So that's the picture we just saw of a bunch of tori shrinking to a lower dimensional torus. But you have the other case, exactly what I was interested in now, right? The case where it's not semi-ample. This is the case where the kernel is not rationally defined modulo the lattice. So then you have this linear subspace in Cn. You can think of it as a distribution in the tangent space of the torus. And this distribution defines a foliation, a holomorphic foliation, and the leaves are not closed. So it's a foliation with non-closed leaves. Here is some kind of a sketch of picture, but of course I couldn't draw more if it's supposed to be dense in this picture, but then you won't see anything. And the Ricci-Feld metrics are just getting shorter and shorter along the leaf of the foliation, and they're not getting shorter in a perpendicular direction, if there is. This torus is pretty small, but for n large, you could have some kernel and some positive definite part, so that doesn't shrink in that direction. So the geometer's exercise for the geometer is to identify the Gromov-Hausdorff limit, and the solution is that it's also a torus, a smaller dimensional torus, related to the dimension of the closure of the leaves. So these leaves are not closed. You can close them and see what's the dimension of the closure. All right, so what can we say about this? So back in the original setup, the class is on the boundary as volume 0, so collapsing, and I do not assume there is semi-ample. So there is not coming from this fibration because we understand the fibration picture very well. And for the moment, I'm gonna take again this stupid segment. So that's because we understand so little in general that you could consider more general paths, but it's really far from anything we can do. So let's just take the segment. So straight segment approaching, and you can write it by picking representative alpha in this form. So you have, again, solution of Monge-Ampère equation. It's always the same equation. The thing that is changing is what is this alpha. And then I posed two conjectures over the years. One, this was very optimistic, is that there should be some closed analytic subvariety, S, such that away from S, you have a C infinity estimates for phi t. And then it would follow that the Ricci-Feld metrics converge smoothly away from this bad set. I mean, maybe modulo subsequences, but presumably even without subsequences. So basically, you should have, again, estimates away from a small bad set. And the second one, more recent, is that at least you should have a global L infinity estimate. So this, again, is, remember, in the original Yau's theorem, the L infinity estimate was what the first key point of the paper. And here you wanted a uniform in T when T goes to 0. So both of these conjectures are true. Let's say in the torus case, that was a stupid, but it's also true in the semi-ample case when you have this vibration. The first conjecture was the theorem with Hein from 2 slides ago. The second one actually was proved much earlier by in Acidieu, Getz, Zeriaki, and Demailly, Pali independently. So using pluripotential theory. More recently, Bingguo, Fong, Song, and Sturm, they have a new proof of this using direct PDE techniques. So these were all known. Yeah, I mean, okay, not when I posed them, but eventually they're true in the semi-ample case. And part B can be actually restated as a question in complex analysis. So if you have a Calabi-Yau with a class on the boundary of the Kähler form, fix some smooth representative alpha, can you find a closed positive current with bounded potentials? So can you find a bounded function such that alpha plus 2 derivative is semi-positive as distributions? So it's just a question in complex analysis. And the word Calabi-Yau is crucial. So if you put here X compare Kähler, this question is known to have a negative answer. So there are counterexamples. So if you want this to be true, you have to use Calabi-Yau. So 2 results about these conjectures. The first result with Simeon Philippe from a few years ago is that the first conjecture is actually completely false. So the conjecture was that you have smooth bounds, C-infinity estimates away from a small, let's say, analytic subvariety. It's not true at all. So there are some K3 surfaces with such classes on the boundary collapsing such that if you approach this direction, exactly the same picture, but the class is different one, then the Ricci-Webb metrics do not converge again in C2. Sorry, this is supposed to be C0, ouch. So sorry, when I write C2, it's C2 for phi. So C0 for the metric, and the same for the previous theorem. So anyway, do not converge smoothly, let's say, for any closed analytic subvariety. So I will discuss this example in more detail in the next slides. This example comes from complex dynamics, and it's very interesting to ask about, again, what is the optimal regularity of this limit? So it's not smooth, but in this case, the potentials phi t do converge to some limit phi 0 in, let's say, in the C0 topology, and the limit is actually Hölder continuous for some small Hölder exponent. This is the theorem of Dean and Sibony in complex dynamics. So one can naturally wonder whether phi 0 is better than Hölder. Presumably it's only Hölder, and that's the sharp one with some critical Hölder exponent, but we don't know. So the first conjecture is false. So the fact that you approach along a straight segment a different point, these two are not the same, makes a huge difference in the results. Even the PDE looks kind of the same superficially. And the second one was, maybe go back to, the second one was, okay, give up smooth estimate, can you at least get a global L infinity bound? And the second one is true with extra assumption on K3 surfaces. So definitely you do not want this assumption. So the K3 has to be projective with no -2 curves and Picard group at least 3. These are all technical hypotheses you need. The class has to be in the real Néron-Severi group, which is a distinguished subgroup of H11, roughly speaking, classes that come from line bundles. So with all these assumptions and restrictions, then you can obtain this L infinity bound. And actually you can construct a family of closed positive currents with continuous potentials, which vary continuously even when you change the class, and they behave well with respect to the automorphism group. So we call this, in our paper, canonical currents from the boundary of the Kähler cone for these K3 surfaces. So these canonical currents, I will also say a little bit how we construct them, but basically the techniques do not have almost no hope to prove the conjecture in general, as I will explain. They also use dynamics, and they're just going to be useful in this case. So the conjecture B for arbitrary K3 and arbitrary alpha is still open, and I will be very much interested to see if it's true or not. And Sibony, Soldatenkov, Verbitsky proved that if alpha is not a rational class, not a multiple of rational class, then actually contains a unique closed positive current. So this current we constructed is the unique one there. And that's definitely completely false if alpha is a rational class. It's actually a semi-ample class. It's a pullback of Fubini study from P1. There are many closed positive currents on P1 in the Fubini study class. So this uniqueness is an even only if the class is irrational. So how are these results proved? So this is the first one. So there are K3s where you don't have smooth convergence. So these K3s are very, very explicit. They were considered by Joachim Wehler implicitly and very explicitly by Barry Mazur and Joe Silverman in the 90s in the context of algebraic dynamics. So you take P1 cross P1 cross P1 and take the zero locus of one homogeneous, multi-homogeneous polynomial of degree 2, 2, 2 in each factor and take it sufficiently generic. So you have to avoid some special polynomials. Then you have X, which is easily seen like an exercise in algebraic geometry. It's a K3 surface. And you can project it in 3 different ways, 2p1 times p1, by dropping one factor. So there are 3 projections. When you project, what are the fibers? The pre-image is exactly take this X and intersect with a line parallel to one of the coordinate lines. And because it's degree 2 in each of them, you can see that generically it's 2 points. So this is a ramified 2-to-1 cover. So all 3 of them are 2-to-1 covers, and therefore there are covering involutions that flip the two sheets. And then you may worry about the ramification, but actually the involution extends holomorphically across the ramification. So you get 3 holomorphic automorphisms of X, which are involutions. And magically, if you compose them, you get an automorphism which is not an involution and it has infinite order. Actually, there's not really magic. The explanation is that the automorphism group of this X is actually isomorphic to the free product of Z mod 2Z, free product Z mod 2Z, free product Z mod 2Z, where the Z mod 2Zs are generated by these 3 involutions. So there is no relation whatsoever among these involutions in the automorphism group. Take a composition in any order of 3, you get an automorphism which has a chaotic behavior. So this is a picture from Kurt McMullen of one of these X with a very explicit polynomial. And there's, okay, you can't see it, but there's the orbit of a point which looks dense. And there is this blue line, which is the stable manifold of the point in the center. So the points which converge there by say, forward iteration. So there's some kind of chaos. I will explain this picture in the next slide. That is a kind of Escher type is related to this example. And so what you do to disprove the conjecture, you take this 222X, take the automorphism as composition of the involutions, take a Ricci flat metric. So when you look at the pullback map, it's a linear map from this vector space to itself. It has a spectral radius, and you compute it, and it's strictly bigger than 1. This is the condition which, by a theorem of Gromov and Yomdin, provides you that the topological entropy of T is strictly positive. So it's a kind of chaotic behavior for dynamics of iterates of T. So this is the key. So you need this spectral radius bigger than 1 to make this construction work. Then you perform something similar to the slide, a few slides before. You pull back the class of a Kähler metric n times, then you divide by lambda to the n. Earlier it was n squared. Now you take this exponentially growing scaling factor, and you can prove that this converges to a class alpha, which is an eigenvector at the pullback. This is just the Perron-Frobenius theorem in linear algebra. And more interestingly, this class, well, is on the boundary of the Kähler cone. It has 0 self-intersection. So it's exactly one of the classes with these collapsing classes that we like. And Cantat proved that it contains a unique closed positive current eta, which therefore, by uniqueness, has to satisfy the same equation as the class. So it's an eigencurrent. It's stretched by the dynamics. So, by the way, if you're really a purist, you can protest that I'm pulling back currents instead of pushing forward currents. Okay. You can push forward also this equation, but in fact, you can define a pullback for these currents, which are closed 1-1 currents. In any case, you can push forward if you want. And then the Ricci flat metrics that defined by the same equation without class. So this again, a family of Ricci flat metrics on this K3. They will converge in the weak topology to a closed positive current in the class, but it's unique. So they have to converge to this eta. And you can write down their cohomology class is basically the straight segment. Oops. Oh, that's bad. Okay, sorry. It's just I think this is going to work. Yes. Just the 1 minus tiny coefficient times alpha plus tiny coefficient. This tiny coefficient is basically the T. So you are exactly in this picture. And if you had smooth convergence away from a subvariety, then this limiting eta will be smooth away from a subvariety. And now that's impossible. So this is a rigidity theorem in dynamics of Cantat-Dupont when X was projective, which these examples I gave you are, but you can also do this for non-projective. And Philip and myself, we found a new proof which also covers the non-projective K3s. And the theorem implies that, says that this eta is smooth, even only if the K3 surface is Kummer, comes from a torus, and also the automorphism T comes from an affine linear map from the torus. And the point is that these 2 are not Kummer if you choose P generic, and so you get a contradiction. So that's why you can't have smooth convergence. If you did, you would be in the super rigid case, which can be classified by some highly non-trivial dynamics work. And by the way, our proof of this dynamics theorem does use the Ricci-Flat matrix of Yau. So it's an application of Ricci-Flat matrix to complex dynamics, which was not something new. So you can also do non-projective K3s, which were constructed by Kurt McMullen in 2000. These was a nice paper using the Torelli theorem. And the theorem also applies to those as well, which you can't really draw. So the last 1 minute, I mentioned the final theorem, which was just rephrased here, namely that although you can't have smooth convergence, you would like to at least have a L infinity bound for the solution, which translates to finding a closed positive current with bounded potentials in this class on the boundary. So we can actually find one even with continuous potential with those assumptions. So the point is, with these assumptions, there is a Kawamata-Morrison-Cohn conjecture, which is actually a theorem of Sturck, which gives you that if you look at the automorphism group, which was this free product ZIMO2, ZIMO2, ZIMO2 free product, this enormous group, it acts on the Néron-Severi group and acts on the Neff cone, the closure of the Kähler cone. And the action of this enormous group has a very nice fundamental domain, which is a rational polyhedral, is this black triangle here. And then the reflection by sigma 1 gives you the reflection across this geodesic. Sigma 2 is the reflection across this geodesic, sigma 3 is the reflection across this, and then when you compose, you get this nice picture here. And the quotient of this fundamental domain, or at least the Kähler cluster with volume 1, is a finite volume hyperbolic orbifold with this dimension. And then to find this current that you want in this class here, what you do is you start from your fundamental domain and write a geodesic ray, hyperbolic geodesic ray from this initial point, which limits to the point that you want. Then you look at this ray, it goes into infinitely many of these chambers, right? So from here to here, you have to apply sigma 1, say. From here to here, I say sigma 3. So you obtain how do you say, a sequence of words in the automorphism group, GI, which tells you how you go. And then if you start with this class and you compose with this sequence of words, and you rescale properly at each step, you will converge to here. And then you need to then pull back the Ricci-Flat matrix and do some careful analysis of how these potentials grow under these iterations. And finally, they will converge uniformly. So that's this trick. This trick only works when you have this Kawamata-Morrison-Cohn conjecture, which is conjecture in higher dimensions, but as the name suggests, is a conjecture. And also, it has several variants. So here you were using a very strong version of the conjecture. The other variants may not be good enough. And in higher dimensions, it's the birational automorphism group that enters. Birational automorphisms are bad because they will destroy the C0 property. So this method definitely does not have any hope in general. So you need some radically new idea to prove or disprove this conjecture in general. All right, I'll stop here. Thank you very much.
Any questions? So on the last slides of your talk, why would you need the rank of Picard group with bigger or equal than 3?
Yeah, there are two technical problems with that. So the one is about you want this automorphism group to be commensurable to a lattice. So up to finite kernel and co-kernel, there should be a lattice. So this is a kind of group theoretic property which only holds in that case. I think if rank Picard is 2 or 1, it's easier, in fact. So I think we could actually delete this one. We just were too lazy to write out the details. This theorem is easier. But this one here is a much more annoying assumption about the no minus 2 curves. Yeah, so yeah, rank Picard, I think maybe we could delete it.
Okay. So other questions? Oh, okay, so if there is no question, let's thank Professor Tosatti again.
Thank you.